Think the Milky Way is huge. There's a galaxy so gigantic it could line up 40 Milky Ways across its face and still spill off the edges. This monster stretches millions of light years wide, packed with trillions of stars, and sits at the heart of a colossal galaxy cluster, slowly swallowing its neighbors over billions of years. Our entire solar system is just a speck inside one spiral arm of the Milky Way, and yet that enormous home galaxy would look almost modest next to this cosmic beast. It's a reminder that the universe is always bigger, stranger, and more extreme than it first appears, and that we're only just beginning to map it. If you want more mind-bending space stories like this, hit subscribe, turn on notifications, and join me as we explore the biggest, brightest, and weirdest objects in the cosmos. When we say that the Milky Way is enormous, we are not using the word casually. Our galaxy is an almost unimaginably large structure, a colossal collection of hundreds of billions of stars, vast clouds of gas and dust, and an enormous halo of dark matter. It stretches across about 100,000 light years, maybe a bit more if you include its faint outer regions. A light year is the distance light travels in 1 year, and light moves at about 300 kilometers per second. In a single second, it could go around the Earth more than 7 times. Let that sink in. Even at that incredible speed, it takes light 100 years just to cross our galaxy from one edge to the other. That already puts the Milky Way in a realm of size that is completely beyond everyday experience. To get a feeling for this scale, it helps to step up gradually. The Earth is about 12,700 kilometers across. The orbit of the Moon is much larger, roughly 770 kilometers around. The distance from the Earth to the Sun is about 150 million kilometers, a unit astronomers call an astronomical unit. Our solar system, if you include the distant orbits of comets in the Oort cloud, may stretch up to a couple of light years across at most, though almost all of its mass is confined to a much smaller central region. Now, place that tiny system inside a galaxy 100 light years wide. You could line up tens of thousands of solar systems, end to end, across the Milky Way, just counting from the Sun outward, and you would still not span the distance from one galactic edge to the other. Even at more familiar speeds, the numbers are staggering. Imagine a jet plane flying at 900 kilometers per hour, fast enough to cross continents in a matter of hours. If you tried to cross the Milky Way at that speed, you would need not just a lifetime, not just the entire history of human civilization, but something like 10 trillion years, far longer than the age of the universe itself. With a car, a train, or a rocket as we build them today, the times are so large they lose meaning. Our technology is utterly dwarfed by galactic distances, yet in the context of the universe, the Milky Way is not the largest galaxy by far. It is more like a mid-sized city in a universe that contains sprawling mega-cities. Astronomers have discovered galaxies that are tens of times larger in diameter than our own, some extending for millions of light years. If the Milky Way's disk is 100 light years across, then a galaxy 40 times that size would span around 4 million light years. That is a number so huge that even astronomers sometimes resort to metaphors simply to talk about it. Consider what 4 million light years actually means. 1 light year is about 9.46 trillion kilometers. Multiply that by 4 million and you get roughly 3. 8 times 10 kilometers, a 3. 8 followed by 19 zeros, written out, that is 38 kilometers. Across that distance, light would take 4 million years to travel. When we look at such a galaxy in the sky, we are not seeing it as it is now, but as it was millions of years ago, because that is how long its light has been in transit. Now compare that to the Milky Way's 100,000 light-year span. A galaxy 40 times larger would be so wide that you could place the Milky Way inside it and still have room left over for dozens of other Milky Way-sized galaxies, side by side, with gaps between them. If the Milky Way were the size of a standard dinner plate, about 25 centimeters across, then a galaxy 40 times larger might be like a table 10 meters wide, a physical object that makes the plate seem almost trivial in comparison. Or imagine shrinking the Milky Way down until it would fit comfortably in the palm of your hand, perhaps as a small coin. That would make the gigantic galaxy about the size of a room, stretching from wall to wall, with your coin barely noticeable on the floor. What is even more impressive is that the Milky Way already contains on the order of a few 100 billion stars. Some estimates hover around 100 to 400 billion. In a galaxy 40 times larger in diameter, especially if it is also more massive, we may be looking at trillions of stars. The total number depends not just on size, but on how densely packed the stars are, yet it gives you an idea of the scale. Each one of those stars could host planets, some of which might be like Earth, orbiting in their own habitable zones, with their own stories of formation, change, and perhaps even life. When you move from hundreds of billions of stars to trillions, the imagination almost buckles under the load. When we say some galaxies are far bigger than the Milky Way, we are not just talking about a gentle increase, like a big city being larger than a small town. We are talking about a step into a new level of magnitude. A galaxy that is 40 times larger in diameter covers 1/600 times the area, because area grows with the square of the radius. If the stellar distribution were similar, such a galaxy might contain hundreds or even thousands of times the stellar content of the Milky Way. And beyond the stars that we see, there is also more gas, more dust, and a much larger halo of dark matter providing the gravitational glue that holds it together. It is also important to understand that when astronomers refer to size, they can mean slightly different things depending on the context. Sometimes they are referring to the diameter over which most of the stars are concentrated, the bright central region, and its visible outskirts. In other cases, they might include faint, extended stellar envelopes that slowly blend into intergalactic space, or the even larger regions traced by radio emission or X-ray emitting gas held in galaxies' gravitational grip. In those broader senses, some galaxy systems truly do span millions of light years. The headline idea that a galaxy can be 40 times the size of the Milky Way captures the essence. There are systems whose reach across space is almost beyond comprehension. From our vantage point on Earth, such a giant galaxy would not look enormous to the naked eye. Distance shrinks apparent size. Something can be incredibly large but so far away that it appears as just a faint smudge in a telescope. That is one of the mind-bending aspects of astronomy. Some of the largest structures in the cosmos look tiny in the sky because they sit so far from us. Only through careful measurements of how bright they are, how their light is spread out, how far their individual components stretch, can astronomers reconstruct their enormous true dimensions. Thinking about galaxies that dwarf the Milky Way also reshapes how we see our own home. It is easy, from inside the Milky Way, to feel as though this is the universe, this swirl of stars, this luminous band across the night sky. For much of human history, people believed the Milky Way might be the entirety of creation, or at least the main stage on which cosmic events played out. Only in the last century did we come to understand that our galaxy is one island among many. Now we know there are billions of galaxies in the observable universe with an incredible range of shapes and sizes, from tiny dwarf galaxies with just a few million stars to giants with thousands of times the Milky Way's stellar mass. If you place the Milky Way on that spectrum, it lands somewhere in the middle. It is not a dwarf, and it is not the most massive galaxy in its neighborhood, but it is far from the largest known. The existence of galaxies 40 times larger in diameter demonstrates that our home is not the upper limit of what nature can build. Gravity, given enough time and enough matter, can assemble structures on scales that outstrip even the huge edifice we live in. There is also a psychological dimension to all of this. Human beings are used to thinking in terms of meters, kilometers, maybe the occasional 1,000 kilometers when we talk about traveling between distant cities. When we first extend that to planetary scales, we already feel a kind of awe. The distance from Earth to the Moon, or from Earth to Mars, is so great that it makes feats like the Apollo missions or the Mars rovers feel heroic. But that entire realm of space travel, as vast as it seems, occupies a mere pinprick compared to the size of a galaxy. Then, when we learn that even this enormous structure, our galaxy, is itself dwarfed by others that are 40 times larger, something profound happens to our sense of scale. We realize that our intuitive sense of big and small is tuned to our everyday lives, not to the universe. Cosmological sizes live on a different scale entirely, and yet, this realization is not meant to diminish the Milky Way or our place within it. Instead, it adds context. The Milky Way is large enough and rich enough to have given rise to a star like the Sun, a planet like Earth, and a species capable of wondering about the size of galaxies in the first place. That an average-sized galaxy can nurture consciousness is itself wondrous. The existence of even larger galaxies simply extends the range of what the cosmos can do. They are demonstrations that the universe is more varied and more expansive than any single example can show. When we say, then, that the Milky Way is already enormous, but some galaxies are 40 times larger, we are compressing a lot into a simple contrast. We are acknowledging the sheer scale of our own galaxy, 100 zeros, 0 light years across, hundreds of billions of stars, while also recognizing that, on the grand stage of the universe, even that is not the final word on size. There are galaxies out there that would make the Milky Way seem, if not small, then at least modest. They stretch across millions of light years, marshal trillions of stars, and hold court within gigantic dark matter halos. The numbers are so huge that no analogy can completely capture them, but they can at least point in the right direction. Imagine driving from one side of your town to the other. That is like crossing a few kilometers. Now, imagine crossing your entire country, maybe a few thousand kilometers. Crossing the Earth's orbit is more like hundreds of millions of kilometers. Crossing the Milky Way jumps to hundreds of thousands of light years. And then one more leap, a galaxy 40 times larger that takes millions of light years to cross. Each step is not just a larger distance, it is a new order of magnitude, a new rung on the ladder of cosmic scale. So the key idea is simple, but its implications are vast. The Milky Way is an immense structure by any ordinary standard, a grand spiral of stars that represents a kind of cosmic metropolis. But in the wider universe, there are even grander cities of stars, galaxies 40 times larger in span, whose bulk and extent challenge our capacity to imagine distance. Recognizing this does not make our galaxy any less impressive. It simply reminds us that in a universe this large, there is always a bigger horizon beyond the one we think we understand. When most people picture a galaxy, they imagine something like the Milky Way, a graceful spiral of stars, with bright arms sweeping outward from a central bulge. That image has become iconic thanks to photographs of galaxies like Andromeda and the famous Whirlpool Galaxy, and it feels, to us, like the default shape of a galaxy. But the universe is under no obligation to match our intuition. When astronomers survey the cosmos, especially the densest regions where galaxies crowd together in huge clusters, they find that the very largest galaxies are often not spirals at all. They are what we call giant ellipticals, enormous, rounded clouds of stars that look more like glowing ovals or spheres than pinwheels. These giants often contain trillions of stars, far more than the few hundred billion in the Milky Way, and they dominate the centers of galaxy clusters like colossal bosses of the cosmic metropolis. To understand why this is so striking, it helps to first get a feel for what makes a spiral galaxy like the Milky Way special. Spirals have a clear structure, a thin, rotating disk with well-defined arms, a central bulge, and usually a halo of older stars and globular clusters surrounding them. The arms are bright because they are full of gas and dust, the raw material for new stars. Blue, hot, short-lived stars are born there in clusters, lighting up the arms and tracing out their elegant curves. The whole system is supported by ordered rotation. Most stars move around the center in a fairly predictable, nearly circular fashion, like cars flowing along lanes in a giant roundabout. Elliptical galaxies, especially the giant ones, are a different story. Instead of a flat disk with arms, they have a more three-dimensional, rounded shape. Think of an egg, a rugby ball, or a slightly squashed sphere of stars. If you look at them in telescope images, they often appear as smooth blobs of light, bright in the center and gradually fading toward the edges, without the obvious spiral pattern of arms or thin, sharp disk we see in spirals. Their stars move in many directions on orbits that cross and intersect. Rather than organized rotation dominating the structure, their shape is supported by the random motions of stars, like a crowded swarm of bees buzzing in all directions. This difference in structure reflects a difference in content and history. The Milky Way still has plenty of cold gas and dust, which means it is actively forming new stars. Regions like the Orion Nebula, for example, are stellar nurseries where gas clouds collapse under gravity and ignite into young, hot stars. Spiral arms are active, ongoing construction zones in the life of a galaxy. Giant ellipticals, by contrast, are often red and dead in astronomers' shorthand. That phrase sounds dramatic, but it simply means that their light is dominated by older, cooler, redder stars, and that they have little cold gas left to fuel new star formation. They are not literally dead, of course. They still contain vast numbers of stars, including many sun-like ones. But the burst of intense star formation that built up most of their stellar mass is largely over. In the present day, they glow with the accumulated light of ancient stars, like an old, well-established city with fewer construction cranes on the skyline. The largest of these ellipticals are truly enormous galaxies like IC 1101, M87 in the Virgo cluster, or the central galaxies in massive clusters such as Able 2029. Some of them stretch more than 1,000,000 light-years across. If the Milky Way is about 100,000 light-years in diameter and a gigantic elliptical is 10 or 20 times that size, you are dealing with an object that could swallow our galaxy and many of its neighbors in the local group with room to spare. Their sheer scale earns them labels like CD galaxies, as central dominant galaxies, or BCGs of brightest cluster galaxies. What gives them this huge, rounded appearance? The answer lies in how they formed and evolved. The current understanding in astronomy is that giant ellipticals are the end products of galaxy mergers, cosmic collisions, and combinations of smaller galaxies over billions of years. When two spiral galaxies collide, their ordered disk structures can be violently disturbed. Their stars, which were once orbiting neatly around each galaxy's center, are thrown into new orbits by the changing gravitational field as the systems interact. Gas clouds slam into each other, compressing and often triggering powerful bursts of star formation, but also heating and dispersing gas so that less is available for future generations of stars. After a major merger, especially if two roughly equal mass spirals combine, the resulting galaxy often no longer looks like a spiral. The distinct arms have been scrambled, the ordered rotation has been partially erased. Instead, you end up with a more rounded, smooth distribution of stars, an elliptical galaxy. Repeat this process again and again over cosmic time, especially in the dense environment of a galaxy cluster, and you can build up truly giant ellipticals. In that sense, they are galaxies made of galaxies, layered histories of past mergers and cannibalized neighbors. This is one reason why the largest ellipticals are usually found in the centers of rich galaxy clusters. Gravity funnels matter toward the deepest parts of a cluster's gravitational well, and those central regions are crowded with galaxies. The biggest galaxy there acts like a gravitational magnet, gradually accreting smaller galaxies that stray too close. Over billions of years, this process of merging, tidal stripping, and slow accumulation grows the central galaxy far beyond the size of a typical spiral. These central giants often have extended, faint halos of stars that stretch far into space, forming what is sometimes called intercluster light, a ghostly, low-surface brightness glow made of stars that have been pulled from their original host galaxies in past interactions. If you could see such a galaxy's full extent with your naked eye, which you cannot, their outer parts are far too dim, you would see not just a bright central blob but a sprawling stellar envelope, blending into the surrounding cluster. That extended envelope is one reason astronomers sometimes quote incredibly large sizes for these systems. They include the very faint outskirts where the central galaxy's influence still holds stars in its grip. From a distance, the contrast between a spiral and a giant elliptical is almost artistic. Spirals are detailed, textured, structured blue patches of new stars here, dark lanes of dust there, clear arms spiraling out. Ellipticals, by comparison, look simpler, a smooth gradient of light, centrally concentrated, with relatively featureless outer regions. But beneath that simple appearance is an intricate internal history. The orbits of stars in an elliptical are tangled records of long past collisions. Subtle changes in the distribution of light, slight twists, asymmetries, or embedded shells can reveal fossil traces of smaller galaxies that were swallowed long ago. The contents of these galaxies also differ in important ways. The stars in giant ellipticals are generally older and more chemically enriched than those in the outer disks of spirals. As generations of stars live and die, they forge heavy elements, carbon, oxygen, iron, and beyond, in their cores and spread them into space through winds and supernova explosions. Over time, that material is incorporated into new stars. In ellipticals, where star formation happened rapidly and early, and then mostly shut down, you end up with a population dominated by old stars that formed when gas was already significantly enriched. That is why elliptical galaxies often appear redder than spirals. Their light is the blended glow of many older, cooler stars. Giant ellipticals also typically host some of the most massive black holes known, right at their centers. For example, the giant elliptical galaxy M87 contains a central black hole with a mass of billions of suns. This is the black hole famously imaged by the Event Horizon Telescope as a glowing ring around a dark shadow. The connection between galaxy mass and black hole mass suggests that the growth of these central monsters is linked to the growth of the galaxy itself, probably through the same merger processes and bursts of star formation that built up the giant elliptical. Another striking difference lies in their gas content. While spirals are rich in cold hydrogen gas, both atomic and molecular, giant ellipticals are often filled instead with hot, thin gas that glows in X-rays. This gas is too hot to easily cool and collapse into new stars, which helps explain why star formation has largely ceased within them. In the centers of clusters, the hot gas pervading the cluster's potential well can be enormous in extent, and the central giant elliptical sits bathed in this hot medium. The galaxy interacts with it through jets and outflows from its central black hole, which can stir and heat the gas, creating beautiful but violent structures observed in X-ray and radio wavelengths. Despite all these differences, it is worth emphasizing that ellipticals and spirals share the same fundamental building blocks: stars, gas, dark matter, and black holes. They are different solutions to the same cosmic problem: how matter, under the influence of gravity and time, organizes itself. For a galaxy of modest environment and relatively quiet merger history, the solution may be a thin rotating disk with well-defined spiral arms. For a galaxy at the heart of a bustling cluster, repeatedly bombarded by neighbors and fed by the infall of smaller systems, the solution is more often a giant elliptical, a huge, rounded cloud of stars with little remaining cold gas. If you could somehow live inside a giant elliptical and look up at its night sky from a hypothetical planet, your view would be very different from our Milky Way sky. Here on Earth, we see the Milky Way as a bright band stretching across the sky, the combined light of countless stars in the disk seen edge on. In an elliptical, there would be no thin disk to create such a band. The stars would be more evenly distributed in all directions, and depending on where you were within the galaxy, the sky might glow with a fairly uniform density of stars, perhaps somewhat denser toward the center, but lacking a strong preferred plane. The entire sky could feel like the inner region of a globular cluster, crowded and luminous by our standards, but spread around you in all directions. Returning to the original point, when we talk about the largest galaxies in the universe, we are, in most cases, talking about these giant ellipticals, not spirals like the Milky Way. Their shapes, rounded, smooth, and featureless at first glance, tell the story of a long, tumultuous history of collisions and mergers. Their immense sizes and masses, often reaching trillions of stars and spanning up to millions of light years, dwarf our already enormous home galaxy. The Milky Way's spiral structure represents youth and ongoing star formation. The giant ellipticals represent age, accumulation, and the settling of matter into massive, stable configurations. Recognizing this adds nuance to our mental picture of the cosmos. The universe is not filled only with elegant spirals that look like the astronomy posters on our walls. It also contains vast, glowing clouds of ancient stars, giant ellipticals, that quietly rule the centers of galaxy clusters. These huge, rounded galaxies remind us that, as impressive as the Milky Way is, it is just one example in a vast zoo of galactic forms, and not the largest animal in that zoo. When we talk about gigantic galaxies, those that dwarf the Milky Way and can be tens of times larger in size and mass, we are not talking about objects that were simply born that way in a single dramatic event. Instead, we are looking at the cumulative result of a long, patient process that plays out over billions of years. At the heart of that process is something astronomers call mergers and, more vividly, galactic cannibalism, galaxies colliding, interacting, and gradually absorbing one another until a true cosmic giant emerges. The universe did not start with huge galaxies already in place. In the early universe, soon after the Big Bang, matter was distributed almost, but not perfectly evenly. Tiny variations in density meant some regions had a little more matter than others. Over time, gravity amplified those small differences. Slightly denser spots pulled in more gas and dark matter, becoming denser still. The first structures to form were relatively small, clumps of dark matter hosting modest amounts of gas and stars, the seeds of the first galaxies. As time went on, these small proto-galaxies did not stay isolated. They existed in a universe where everything pulls on everything else, and gravity naturally draws smaller systems together into bigger ones. This is what astronomers call hierarchical structure formation. Small things form first, then merge to make larger things, which then merge again, and so on. Gigantic galaxies at the present day are thus the inherited end products of countless earlier combinations. When we say that galaxies merge, it is easy to imagine them smashing into each other like solid objects. But a galaxy is mostly empty space. The stars inside are spaced so far apart that even in a direct collision between two galaxies, individual stars almost never hit each other. What really happens is more subtle and more interesting. The gravitational fields of the two galaxies interact, tugging on each other's stars, gas, and dark matter. Over time, this reshapes their internal structure. Picture two spiral galaxies, like the Milky Way, slowly approaching each other. As they get closer, their gravity begins to distort their shapes, pulling out long, graceful streams of stars and gas called tidal tails. Their disks warp, their spiral arms twist, and stars that once followed nearly circular orbits are thrown onto new, more chaotic paths. The galaxies may plunge through each other and swing apart, only to be pulled back together again for another pass. With each encounter, they lose orbital energy to the random motions of their stars and to their dark matter halos. Eventually, they settle into a single, larger galaxy. Astronomers distinguish between major mergers and minor mergers. A major merger happens when two galaxies of roughly similar mass collide and combine. These are violent events on a galactic scale. The ordered rotation that maintained a spiral structure can be disrupted so thoroughly that the final product no longer looks like a spiral. Instead, it becomes a more rounded, elliptical galaxy. Gas clouds slam into each other, compressing and igniting intense bursts of star formation. Those bright, short-lived bursts can consume much of the galaxy's remaining cold gas in a relatively brief period, astronomically speaking. Minor mergers, on the other hand, occur when a large galaxy swallows a much smaller one, a dwarf companion, for instance. These are quieter, but far more frequent. The larger galaxy exerts a strong tidal pull on the smaller one, stripping away its outer stars and gas, stretching it into a stream, and gradually absorbing its contents. Over billions of years, a big galaxy can cannibalize dozens or even hundreds of smaller companions. Each addition may only change the host slightly, but the cumulative effect can be enormous. This is what astronomers mean by galactic cannibalism. It is especially common in galaxy clusters, where many galaxies are packed into a relatively small region of space and orbit around the cluster's common center of gravity. Near the very center of the cluster sits a dominant galaxy, typically a giant elliptical. This central galaxy is in a prime position to capture others. As smaller galaxies orbit through the cluster, they experience a drag force known as dynamical friction. Their motion through the background of other stars and dark matter creates a kind of wake, which saps their orbital energy and gradually causes them to spiral inward toward the cluster's center. There, the giant galaxy waits. Over time, these infalling galaxies are shredded by the tidal forces of the central giant. Their stars are peeled off and either join the giant's outer halo or float freely through the cluster as intracluster light, a faint glow between the more easily seen galaxies. Their gas may be stripped and heated, contributing to the hot, X-ray emitting gas that permeates the cluster. Their dark matter is pulled apart and added to the enormous dark matter halo in which the whole system resides. The visible galaxy at the cluster's heart thus grows both in mass and in physical size, surrounded by a vast, dim envelope of stars that were once parts of many different galaxies. As this process repeats over and over, the central galaxy can become a true monster. Its stellar component may extend over 1 million light-years or more. Much of its growth in radius happens not so much in the dense, bright core as in the addition of this diffuse outer envelope made of cannibalized satellites. In simulations and deep observations, we see that the outskirts of such giants are patchworks of debris, streams, shells, and plumes left behind by past accretion events, slowly mixing into a smoother halo over time. Our own Milky Way offers a small-scale, local example of this kind of cannibalism. It is not a giant elliptical at the center of a cluster, but even as a mid-sized spiral in a relatively small group of galaxies, it is actively eating its neighbors. The Sagittarius dwarf spheroidal galaxy is currently being torn apart by the Milky Way's gravity, its stars stretched into a looping stream that wraps around our galaxy. The Gaia Space Observatory has revealed that a significant fraction of the Milky Way's halo stars were once part of another galaxy, now referred to as Gaia Enceladus, or the Gaia Sausage, that merged with us billions of years ago. The large and small Magellanic Clouds, visible from the southern hemisphere, are also expected to eventually be consumed by the Milky Way in the far future. An even more dramatic event awaits. In about 4 to 5 billion years, the Milky Way and the Andromeda Galaxy, our nearest large neighbor, are expected to collide and merge. Both are spirals of roughly similar mass, so this will be a major merger. Simulations suggest that after a long and complex dance of close passes, tidal distortions, and starburst episodes, the two will settle into a single, much larger galaxy. It will likely have a more elliptical structure than either of the original spirals, with stars from both systems mixed together. The central black holes of each galaxy will spiral toward one another and eventually merge, creating an even more massive black hole at the heart of the new galaxy. This future event is a small-scale version of what has built the truly gigantic galaxies at the centers of rich clusters. Those central giants have not just one major merger in their history, but many. They have swallowed large companions and countless dwarf galaxies, gradually building up their enormous masses. Every merger has also been an opportunity to feed their central black holes, as gas is funneled toward the core. When enough gas falls in, the black hole can light up as an active galactic nucleus, emitting powerful jets and radiation that can heat surrounding gas and help shut down further star formation. In that way, galactic cannibalism and black hole growth are intertwined in shaping the life story of giant galaxies. The observational evidence for this merger-driven growth is strong. Deep images of nearby giant ellipticals reveal ripples, shells, and faint streams around them, signatures of past interactions. In clusters, we see diffuse intracluster light that cannot be neatly assigned to any single galaxy, the remnants of stars stripped from their original homes. In more distant galaxies, we catch systems in the act of merging, pairs or groups of galaxies distorted and tangled, with long tidal tails and knots of intense star formation. Computer simulations of galaxy formation, based on the laws of gravity and the presence of dark matter and gas, naturally reproduce such features when they include frequent mergers and accretion. From a theoretical point of view, this makes sense. The cosmological model that best fits the day, to one in which the universe is dominated by dark energy and cold dark matter, predicts that structure grows hierarchically through the merging of smaller dark matter halos into larger ones. Galaxies live inside these halos, so they too grow by merging. The largest galaxies live in the most massive halos, at the intersections of the cosmic web where filaments of matter converge. There, the density of galaxies is highest, the chances of close encounters greatest, and the opportunities for cannibalism most abundant. The term cannibalism might sound violent or unnatural, but on cosmic timescales it is simply the way gravity operates when many massive objects share the same region of space. Smaller galaxies, losing energy through dynamical friction and tidal interactions, fall inward and are consumed by larger ones. No laws are broken, rather, the universe is following a natural path toward greater clustering of matter. Over time, the number of distinct galaxies in a cluster may decrease as more and more are swallowed into the central giant or torn apart into diffuse light. In the end, when we look at a gigantic galaxy 40 times larger than the Milky Way, we are seeing the fossil record of this entire history written in stars. Its enormous size and mass are not the result of a single event, but of countless mergers, both large and small. Each dwarf galaxy it has digested, each spiral it has absorbed, has left some imprint in its structure and its stellar populations. The smooth glow of its light hides a story as rich and intricate as a layered geological formation, with each layer a past galaxy that no longer exists as a separate entity. Understanding mergers and galactic cannibalism, then, is essential to understanding why such giants exist at all. Without these processes, galaxies would remain closer to their original, smaller sizes. Gravity, however, never stops working, and given enough time, it will gather matter into ever larger configurations. Gigantic galaxies are the natural culmination of that process, the largest visible structures made of stars, assembled one meal at a time over the entire history of the universe. When we look at a gigantic galaxy 40 times larger than the Milky Way, we are only seeing the tip of a vastly larger iceberg. The visible stars, gas, and dust are wrapped inside an enormous, invisible structure of dark matter called a halo. This dark matter halo does not simply sit there as a passive container. It plays an active, central role in how such a galaxy forms, grows, and reaches its extraordinary size. Without these halos, the universe as we know it, filled with galaxies of different sizes and shapes, would not exist. Dark matter itself remains one of the great mysteries of modern physics. We cannot see it directly because it does not emit, absorb, or reflect light. Yet, we know it is there because of its gravitational effects. When astronomers measure how fast stars orbit in galaxies, or how galaxies move within clusters, they find that visible matter alone cannot provide enough gravity to hold everything together. The outer parts of galaxies rotate too quickly, clusters would fly apart if only the observed stars and gas were present. The solution is that there must be additional mass we cannot see, outweighing normal matter by about 5 to 1. This unseen component is what we call dark matter. In a galaxy, dark matter is not scattered randomly. It forms a roughly spherical halo that extends far beyond the visible disk or central bulge. In the Milky Way, for example, the disk of stars is about 100 light-years across, but the dark matter halo may stretch several 100,000 light-years or more, perhaps even approaching a million light-years in diameter when you include its faint outer regions. For a gigantic galaxy 40 times larger than the Milky Way, its halo is correspondingly stupendous, an immense bubble of dark matter enveloping a region of space where dozens of Milky Way-sized galaxies could easily fit. These halos arose very early in the universe. Shortly after the Big Bang, the universe was filled with a nearly uniform mixture of dark matter and ordinary matter, mostly hydrogen and helium, with tiny variations in density. Dark matter, which interacts mainly through gravity and not through electromagnetic forces, began to clump under its own gravity faster than ordinary matter, which was tied more closely to radiation. In the early hot universe, over time, dark matter gathered into dense regions, what we now call halos. These halos provided the gravitational wells that pulled in gas, allowing galaxies to form in their centers. The size and mass of a dark matter halo are crucial. A more massive halo has a deeper gravitational well, meaning it can pull in more gas from its surroundings and also hold onto that gas more effectively against processes that might try to heat it up or blow it away. As the universe evolved, small halos merged to form larger ones, and those larger ones merged into even larger structures. This hierarchical buildup of halos mirrors the hierarchical buildup of galaxies themselves. Gigantic galaxies live inside the most massive halos, often at the nodes of the cosmic web where filaments of matter intersect. When gas falls into a dark matter halo, it gains kinetic energy and heats up. In smaller halos, the gas can cool relatively quickly, radiating away its heat and condensing into a rotating disk where stars can form. In extremely massive halos, the kind that host enormous galaxies and clusters of galaxies, the story is more complex. The infalling gas can be heated to extremely high temperatures, forming a hot, diffuse atmosphere that fills the halo. This gas glows in X-rays and can take a long time to cool. Some of it will eventually cool and sink toward the center, where it can fuel bursts of star formation in the central galaxy. Other parts remain hot, supported against collapse by thermal pressure and sometimes by energy feedback from growing supermassive black holes at the center. The key point is that without a massive halo, you cannot build a truly giant galaxy. The halo is the framework around which the visible galaxy is assembled. Its mass sets a kind of budget for how much gas can fall in, and ultimately how many stars can form. Observations and simulations show a strong correlation between the mass of a halo and the stellar mass and luminosity of its central galaxy. The brightest cluster galaxies, the enormous ellipticals at the centers of galaxy clusters, sit inside the most massive known halos. Their dark matter halos are not just galaxy-sized, they are cluster-sized, extending millions of light years and enclosing enough mass to bind hundreds or thousands of galaxies. Dark matter halos also govern mergers, which, as discussed earlier, are a principal way galaxies grow. When two halos pass near each other, their mutual gravity can pull them together, merging their dark matter content into a larger halo. The galaxies that had been at the centers of the old halos now find themselves inside a single merged halo, where they may eventually collide and combine. In that sense, halo mergers drive galaxy mergers. The growing dark matter skeleton sets the stage on which visible structures collide and rearrange themselves. In the densest regions of the universe, where many massive halos lie close together, they can eventually combine into a single, extremely massive halo that contains a whole galaxy cluster. The central region of that halo hosts the most massive galaxy in the cluster, embedded within a cloud of hot gas and surrounded by numerous satellite galaxies orbiting in the same gravitational potential. Over billions of years, dynamical friction slows down the orbits of some of those satellites, causing them to sink toward the center, where tidal forces tear them apart and add their stars to the central giant. All of this happens inside the deep well of the shared dark matter halo. The structure of halos themselves influences galaxy properties. According to simulations, dark matter halos follow a fairly universal density profile. They are denser in the center and become more diffuse outward, with a specific pattern often described by the NFW profile, named after Navarro, Frank, and White. The inner concentration of dark matter affects how fast stars orbit near the center of a galaxy, how tightly bound the galaxy is, and how susceptible it is to tidal disruption. The outer halo's extent determines the region from which gas and small satellites can be accreted. In massive halos, the sheer volume encompassed can be vast, meaning the central galaxy has access to an enormous reservoir of mass over cosmic time. Dark matter also plays a role in shielding galaxies from their surroundings. In less massive systems, processes like supernova explosions or energy output from a central black hole can blow gas out of the galaxy, especially from its outer regions. If the overall gravitational potential is shallow, that gas may escape entirely, reducing the galaxy's ability to make new stars. In a very massive halo, however, the escape velocity is high. Gas that is heated and blown outward may still remain bound to the system. It can cool later and fall back in, sustaining star formation or feeding the central black hole over longer periods. This recycling process is more effective in deeper potential wells, making massive halos more resilient to internal feedback processes. At the same time, the largest halos can actually suppress star formation in a different way. Because infalling gas is shock heated to very high temperatures, it can form a stable, hot atmosphere around the central galaxy. Unless this gas can cool efficiently, it will not collapse to form new stars. Energy from an active central black hole can keep the gas hot by injecting power through jets and radiation, a process known as AGN feedback. In many giant ellipticals, star formation appears to have shut down long ago, leaving them dominated by old, red stars. In such systems, the dark matter halo has allowed them to assemble huge masses, but the combination of a hot halo and AGN feedback prevents further rapid growth of the stellar component, locking them into a massive, relatively quiescent state. When astronomers map the large-scale distribution of galaxies in the universe, they see a cosmic web, filaments of galaxies and gas stretching between dense nodes with voids in between. This structure is really the visible trace of an underlying web of dark matter. The nodes where filaments intersect are where the biggest halos, and thus the biggest galaxies, tend to reside. There, streams of gas and smaller halos flow inward along the filaments, feeding the central giants. Over billions of years, this continuous supply, governed by the dark matter scaffolding, allows these galaxies to become truly enormous, both in terms of their stellar content and their spatial extent. The influence of dark matter halos is not just a theoretical idea. It is strongly supported by observations. Gravitational lensing, where the mass of a galaxy or cluster bends the path of light from background objects, allows astronomers to map the mass distribution of halos, even though the dark matter itself is invisible. These maps show that the mass in a cluster is overwhelmingly dominated by dark matter, with the luminous galaxies and hot gas embedded inside. In systems with giant central galaxies, lensing confirms that they sit at the bottom of a very deep gravitational well, exactly what we would expect if they occupy the centers of the most massive halos. Rotation curves of spiral galaxies, measurements of galaxy velocities in clusters, and the cosmic microwave backgrounds, precise patterns of fluctuation, all point to the same conclusion: dark matter halos provide the fundamental gravitational framework of structure in the universe. Galaxies, even the biggest ones, are luminous decorations on this invisible skeleton. Their sizes, shapes, and histories are profoundly guided by the halos they live in. So when we say that dark matter halos play a crucial role in building gigantic galaxies, we are really saying they are the architects of cosmic scale. A galaxy 40 times larger than the Milky Way can only exist because it sits in an extraordinary halo, one that has pulled matter from a great volume of space, merged with many other halos, and held onto its contents over billions of years. The visible giant is the bright core of a much larger, darker entity, and its story cannot be told without that unseen partner. When astronomers say that a particular galaxy is millions of light years across, or 40 times the size of the Milky Way, they are not pulling those numbers from thin air. They are the end result of a chain of careful measurements and physical reasoning. The challenge is this: we cannot travel to a galaxy and stretch a tape measure across it. All we ever receive from distant galaxies is light photons collected by telescopes. From that limited information, astronomers have to infer how big the galaxies actually are. The measurement process rests on two key ingredients: how big the galaxy appears on the sky, its apparent or angular size, and how far away it is, its distance. Once you know both, you can connect them with basic geometry to get the galaxy's true size. On top of that, astronomers use observations in different wavelengths, optical, infrared, radio, X-ray, to reveal parts of the galaxy that might be invisible or faint in ordinary visible light. Together, these ideas let us say with some confidence that certain galaxies stretch across regions of space vast enough to fit many Milky Ways side by side. Start with apparent size. If you look at a galaxy through a telescope, it occupies some small patch of the sky. We describe that patch in angular terms: degrees, arcminutes, or arcseconds. The full moon, for example, is about half a degree across, or about 30 arcminutes. Most galaxies, even the large ones, look much smaller than that to us because they are so far away. A typical distant galaxy might be a few arcseconds across, a tiny speck compared to the moon. Astronomers examine images from telescopes and use software to trace how far the galaxy extends from its center before it fades into the background sky. That gives them an angular diameter, or more often, some characteristic angular radius. However, galaxies do not have sharp, well-defined edges. Their brightness gradually decreases from the center outward, and at some point the galaxy becomes too faint to distinguish from the sky background. Where do you say it stops? To answer that, astronomers use conventions. For example, they might define the size of a galaxy as the radius at which its surface brightness drops below a certain threshold, or they might measure the effective radius, the radius within which half of the galaxy's total light is contained. Another common approach is to fit the galaxy's light profile with a mathematical function, like a Sayesic profile, and then quote a characteristic radius from that fit. Different studies may adopt slightly different definitions, but the basic idea is the same: measure how far the galaxy's light extends in angular terms. Once you have the angular size, the crucial next step is the distance. Without distance, an angular size is ambiguous. A small object nearby can have the same apparent size as a huge object far away. So they are seals to verti over are the moon. Entire the future coin fisu tiny. The moon is enormous, yet they can look the same size on the sky from your vantage point. For galaxies, astronomers must figure out how far away they are so they can convert angular size to physical size. Astronomers use a cosmic distance ladder, a series of methods that work at different scales and overlap to check each other. For nearby galaxies, they can sometimes resolve individual stars and use objects whose intrinsic brightness is known, standard candles, to judge distance. Cepheid variable stars, for instance, have a well-established relationship between their pulsation period and their true luminosity. By measuring how bright a cepheid looks and comparing that to how bright it ought to be, astronomers can determine how far away it must be. The same principle applies to other candles like our Arlary stars or the tip of the red giant branch. For somewhat more distant galaxies, where individual stars blur together, astronomers might use Type Ia supernova as standard candles. These are powerful stellar explosions whose peak brightnesses follow a pattern that can be calibrated. If a Type Ia supernova goes off in a distant galaxy, its apparent brightness provides a measure of that galaxy's distance. Other techniques include surface brightness fluctuations, subtle pixel-to-pixel brightness variations in a galaxy's image that get smoother with distance, and empirical relations like the Tully-Fisher relation for spiral galaxies linking rotational speed to luminosity, or the Faber-Jackson and fundamental plane relations for elliptical galaxies linking velocity, dispersion, and size to luminosity. All of these convert observable quantities like brightness or speed into an estimate of distance. For very distant galaxies, those far out in the expanding universe, astronomers rely heavily on redshift. As space expands, light traveling through it is stretched to longer, redder wavelengths. The amount of redshift in a galaxy's spectral lines tells us how fast it is receding from us, on average, due to cosmic expansion. Using the equations of cosmology and a measured value of the Hubble constant, which relates a galaxy's recession velocity to its distance, astronomers can convert redshift into an approximate distance scale. At large distances, this is not a simple linear relation. It involves the full cosmic expansion history and the effects of dark energy. But with a standard cosmological model, you can compute the angular diameter distance to a galaxy from its redshift. With both the angular size and distance at hand, geometry does the rest. For small angles, the physical size of an object is approximately equal to its distance multiplied by the angle measured in radians. More precisely, you can use the relation size equals distance times tan angle. Because the angles involved are tiny, the tangent is almost equal to the angle itself in radians, making the approximation very accurate. So, for example, if a galaxy appears 10 arcseconds across and lies at a distance of 500 million light-years, you can convert 10 arcseconds to radians and multiply by 500 million light-years to get physical diameter. Repeat this for many galaxies, and you begin to see which ones truly rank among the giants. Cosmology adds a twist. The relation between angular size and distance is different in an expanding universe than in everyday Euclidean space. Beyond a certain redshift, galaxies at greater distances can actually appear larger in angular size, again, due to the way light paths and expansion interact. To handle this properly, astronomers do not just plug numbers into a simple school geometry formula. They use the cosmological angular diameter distance appropriate for the redshift of each galaxy, computed from the underlying cosmological model. This is why knowing the overall properties of the universe, its expansion rate, matter content, and dark energy density, is so important for precision size measurements. So far, we have talked about galaxy sizes mostly in terms of the stars we see in visible light. But galaxies are multi-component systems, and not all of their parts shine brightly in the same wavelengths. This is where multi-wavelength observations become vital. A galaxy can appear one size in optical light, another in ultraviolet, a larger size still in radio wavelengths, and larger yet if you consider its gravitational influence inferred from dynamics or lensing. When astronomers say a galaxy is millions of light-years across, they focus their definition. Are they talking about the stellar component, the extended halo of faint stars, the hot gas or radio lobes from the central black hole? Optical and near-infrared observations mostly trace starlight. They show the bright bulge and disk, the regions where stars are densely packed, and the outer halos where the light gradually fades. To see very faint outskirts, astronomers take long exposure images with large telescopes and use careful data processing to subtract the night sky background and instrumental noise. Deep optical imaging has revealed that some galaxies, especially giant ellipticals in clusters, have extended envelopes of stars that were invisible in earlier, shallower surveys. These halos can extend far beyond the bright core, significantly increasing the estimated size of the galaxy's stellar component. In the ultraviolet, telescopes like Galaxies have shown that some galaxies have sprawling regions of recent star formation beyond what is obvious in optical light. These extended UV disks reveal that star formation can occur well into the outskirts, pushing the effective star-forming radius farther out. Radio observations provide another perspective. Neutral hydrogen gas in galaxies emits radio waves at a characteristic wavelength of 21 centimeters. Mapping this emission shows that the gas disks of many galaxies extend much farther than the starlight does, sometimes 2 or 3 times the radius of the optical disk. For giant galaxies, especially those at the centers of clusters, radio telescopes also pick up enormous jets and lobes of relativistic particles launched by the central supermassive black hole. These structures can extend millions of light years into intergalactic space. In some spectacular radio galaxies, the radio lobes define a size far larger than the galaxy's visible stars. When people talk about record-breaking giant radio galaxies, they are often referring to the extent of these radio lobes, not just the stellar body. X-ray observations from satellites like Chandra or XMM Newton reveal the diffuse, hot gas that bathes galaxy clusters and giant ellipticals. This gas is often contained by the same gravitational well as the central galaxy and can extend over megaparsec scales, millions of light years. By studying its X-ray emission, astronomers can map how far this gas reaches and thus get a sense of how large the overall system is, including the galaxy and its gaseous halo. Even gravitational lensing, which measures how a galaxy or cluster bends the light from background objects, can enter the picture. Lensing shows the reach of a system's gravitational field, which is primarily determined by dark matter. While this does not give a size in the same visual sense as a diameter of stars does, it tells us over what spatial scales the galaxy's mass dominates. In some sense, this is the most fundamental size, the region of space significantly under the galaxy's gravitational influence. Putting all of these pieces together, optical, infrared, ultraviolet, radio, X-ray, lensing, astronomers build a composite picture of a galaxy's extent. They decide what they mean by size. For the purpose at hand, is it the radius containing half the light, the radius where the surface brightness drops to some level, the full reach of the stellar halo, or the span of radio lobes? Different choices can yield different numbers, but the methods are consistent and grounded in the physics of light and gravity. For the specific case of gigantic galaxies claimed to be tens of times larger than the Milky Way, astronomers typically refer either to the extent of the stellar envelope in deep optical images, or to the full span of radio or X-ray traced structures associated with the galaxy. They carefully measure how far this light or emission extends, convert the angular size to a physical one using well-established distance estimates, and then compare the result to the Milky Way's approximate 100,000 light-year diameter. That is how we arrive at statements like this galaxy is 40 times larger than the Milky Way, not as a guess, but as the end product of a chain of measurements and calculations, all rooted in careful observation of the faint light that has traveled across the universe to reach our telescopes. When we learn that there are galaxies 40 times larger than the Milky Way, the first reaction is often simple amazement at the numbers. Millions of light years across, trillions of stars, it feels like a record in some cosmic Guinness book. But if we stay with that thought a little longer, it becomes something deeper. These gigantic galaxies are not just trivia, they reframe where we stand in the universe. They are a kind of mirror, held up on the largest possible scale, showing us both how small we are and how extraordinary it is that we can even know that. For a long stretch of human history, it was natural to assume that we were at the center of things. The sky turned overhead, the stars wheeled around us, and the sun rose and set for our world. Even after we accepted that Earth orbits the sun, the Milky Way still seemed like the main stage of creation. It was the great river of light across the sky, the home of all the stars we could see. Only in the last century did we discover that the Milky Way itself is just one galaxy among countless others. Now, when we add the fact that there are galaxies dozens of times bigger than ours, another quiet shift happens. The Milky Way is not the universe. It is not even the largest kind of galaxy the universe can make. This realization is a lesson in humility. Our galaxy, with its hundreds of billions of stars, feels unimaginably vast from the surface of a single planet. But in the ledger of the cosmos, it is mid-sized, perhaps even modest. There are enormous ellipticals in distant clusters whose starry halos make the Milky Way look like a provincial town next to a sprawling metropolis. Just as Earth lost its status as the center of the solar system, and the Sun lost its status as a special star, the Milky Way loses its status as a cosmic giant. Each of these steps nudges us gently away from the notion that we occupy a privileged perch in the universe. That nudge can be uncomfortable if we are attached to the idea of centrality. It is not always easy to accept that we live on an ordinary planet, orbiting an ordinary star, in the outer suburbs of an ordinary galaxy, which itself is overshadowed by far larger structures. Our physical scale and location, in other words, are not special, but humility in this sense does not mean insignificance. It means clearing away assumptions so we can see more clearly. The universe is what it is, whether we find that flattering or not. Galaxies 40 times larger than the Milky Way are one of the universe's ways of reminding us that reality is not built to match our ego. At the same time, these giants also reveal something about our context that goes beyond size. They show where the real centers of gravitational power lie in the cosmos. The largest galaxies sit at the intersections of the cosmic web, where filaments of dark matter and gas come together. They anchor enormous clusters of galaxies, surrounded by hot gas and bathed in dark matter halos that span millions of light years. When we map the universe on its largest scales, these regions stand out like cities connected by highways of galactic filaments. The Milky Way, by comparison, is like a small town on a side road. To know that is to understand that our local neighborhood is just one modest node in a far larger cosmic architecture. Yet, if humility is one half of the emotional response, the other half is wonder, because as soon as we say, we are small, we are forced to admit something else. Despite that smallness, we have figured all this out. On a planet that is, cosmically speaking, a speck of dust, a species that has existed for only a moment in cosmic time has measured the sizes of galaxies millions of light years away. We have detected the faint light from their stars, mapped the halos of their gas, traced their radio jets, and used physics to turn those observations into distances and diameters. We are tiny in space and fleeting in time, but our reach through curiosity, mathematics, and instruments is not tiny at all. That contrast is one of the most remarkable facts about our situation. We are not large, but we are capable of large thoughts. We cannot cross our own galaxy with rockets, let alone visit a giant elliptical at the heart of a distant cluster. But with telescopes and equations, we can let the universe come to us through light. Those same photons that left a giant galaxy millions or billions of years ago now fall on our detectors. We measure their wavelengths, their angles, their intensities, and from them we reconstruct the story of places we will never physically touch. The galaxies that humble us by their size also elevate us by what they reveal about our mind's ability to roam. There is also something quietly unifying about this perspective. From the vantage point of an enormous galaxy 40 times larger than the Milky Way, our particular disputes and divisions would be invisible. The borders we draw on maps, the conflicts we wage, the hierarchies we invent, all of them vanish against a backdrop in which even entire galaxies are just points of light. This does not make our problems unimportant to us, but it does put them in a new frame. The fact that we share a small planet around an ordinary star in a mid-sized galaxy begins to feel like a reason for solidarity rather than separation. Our common situation is much more fundamental than our differences. Gigantic galaxies also sharpen our appreciation for how rare and precious our immediate environment is. Vast as those systems are, they are, as far as we know, mostly deserts, star after star, many with lifeless worlds, all separated by distances that defeat easy travel. Our own region of the Milky Way happens to include a rocky planet with liquid water, a stable sun, and a biosphere that has been evolving for billions of years. To recognize that there are galaxies so large they make the Milky Way look small does not diminish the value of the thin film of life on this planet. If anything, it heightens it. In a universe where you can have 1 trillion stars and still, perhaps, no one to look back at them, the existence of any observers at all is astonishing. In this sense, the discovery of enormous galaxies is part of a larger story, in which every expansion of our physical horizons has been matched by an expansion of our mental and moral horizons. When we realize the Earth is a sphere, not a flat plane, our conception of the world changed. When we discovered other planets, we had to rethink what a world even is. When we came to understand that stars are suns, and that galaxies are vast collections of such suns, our idea of the heavens transformed again. Each step has asked us to see ourselves differently, smaller in scale but larger in perspective. The recognition of galaxies 40 times larger than ours is simply one of the most recent steps. There is an artistic and emotional dimension to this as well. Images of giant galaxies with their smooth glowing halos and the tiny companion galaxies scattered around them have a kind of quiet majesty. They invite contemplation. We know, intellectually, that the bright core may contain a supermassive black hole, that the halo is a fossil of countless mergers, that the cluster around it is tied together by dark matter. But beyond the science, there is a feeling that we are looking at something ancient, immense, and indifferent to us, yet open to our understanding. It is the same feeling that people have always had under starry skies, now given sharper shape by what we have learned. Humility and wonder together can be a powerful combination. Humility alone can slide into a sense of futility. If we are so small, does anything we do matter? Wonder alone, without humility, can become a kind of superficial thrill, a momentary wow, without deeper reflection. But when we hold both at once, a different attitude emerges. We see that our lives are brief, and our planet is tiny, and that this does not erase meaning, it contextualizes it. We are local phenomena in a vast universe, but within our locality we have responsibilities. To each other, to other living things, to the fragile systems that sustain us. Knowing that there are galaxies 40 times larger than the Milky Way does not tell us how to live, but it quietly suggests that we live in a way that acknowledges scale, fragility, and connection. These gigantic galaxies also testify to the power of shared human effort. The knowledge that they exist, that they are as large as they are, did not come from one person, one culture, or one century. It is the product of generations, the development of optics, the refinement of mathematics, the invention of spectroscopy, the launch of space telescopes, the work of observers and theorists around the world. When we say this galaxy is 40 times larger than the Milky Way, we are reciting a fact that encodes thousands of hours of observation, analysis, and debate. In that sense, the galaxies not only show our place in the universe, they show what we can do when we extend our curiosity beyond immediate needs. In the end, gigantic galaxies serve as markers on the map of reality. They tell us how far nature can go in building structures out of matter and gravity. They highlight the mid-sized nature of our own home galaxy. They underscore the thinness of our physical presence and the breadth of our intellectual reach. They remind us that the universe has been creating and merging galaxies for billions of years before we appeared, and will continue to do so long after we are gone. And in doing all of this, they invite us into a certain posture, small in body, ambitious in mind, grounded by humility, lifted by wonder,